Look at this assembly line. Modern engineering organizations rarely build single-point solutions anymore. Whether it's automotive, aerospace, or defense, they manufacture highly varied product lines, meticulously tailored to distinct regional regulations and fragmented market demands. But managing this variation using traditional systems engineering, specifically the older ISO 26550 standard, introduced a fatal structural flaw. It relied heavily on manual application engineering. When a new product variant was needed, engineers utilized a method known as clone and own. They would physically copy the core domain assets, the base design and code, and manually modify them to fit the specific requirements of that single new product. This diagram shows what happens next. You have a timeline of requirements, SysML blocks, code, and test scripts. By manually duplicating assets for variants A, B, and C, the system fractures into a chaotic, tangled web of broken links. A specific requirements tag for a braking mechanism is copied for a new model, but it loses its connection to the corresponding C code block, hidden behind an ifdef statement, and the cloned test folder meant to validate it. Traditional version control branches and forks function for a single software application, but when applied to complex, multi-domain system product lines, this disconnection causes lifecycle validation costs to multiply. To solve this, the industry introduced ISO 26580 feature-based product line engineering. This methodology discards manual product configuration, replacing it with an automated logical factory. Under this framework, the traditional division of labor between domain engineering, building the core, and application engineering, customizing the product, is eliminated. Instead, 100% of the engineering effort, every design choice, code update, and test script, is shifted upward into a centralized domain. The objective of this centralization is to stop treating individual product variants as permanent engineering artifacts. The factory treats them as disposable outputs, generated on demand by a central engine. Engineers stop managing physical files scattered across hundreds of branches and begin managing abstract logical features. This brings us to the first layer of the PLE factory architecture. This visual represents a clean, vertical architectural stack, starting with this central foundational block, the shared asset superset. The superset acts as a zero-duplication repository. It contains all potential lifecycle content for every possible product in the portfolio. No physical copies exist outside of this block. Inside the superset, the assets are divided into two categories. First is common content. These are the unconditional assets, the base platform architecture included in every single manufactured product. Embedded within that common content are variation points. These are the conditional elements that change, activate, or disappear based on the specific requirements of a given product. These variation points are not manual placeholders or text notes left for developers. They are formal, machine-readable logic gates. By enforcing a singular source of truth for all code and design elements, the superset prevents the traceability failures that consistently plague the clone and own method. The second layer of the factory is the feature catalog. This serves as a clean, overarching dictionary that defines the entire product line's capabilities. A feature here might be a regional compliance restriction, like European emission standards, or a specific hardware addition, such as adaptive cruise control. The architecture requires strict formal mapping. Every abstract feature in the catalog is physically wired to specific variation points inside the superset. When an organization needs to build a specific vehicle or system, they create a bill of features, a precise selection of options chosen from the catalog for that single member product. The bill of features acts as the exact mathematical recipe required to extract one unique, fully functioning product from the complexity stored inside the superset. To execute that recipe, we use the Configurator engine. This is the central automated processor. The Configurator reads the bill of features, slices through the superset, and executes rules of omission and selection across all variation points. The engine outputs a complete product instance, containing precise requirements, exact code files, and perfectly aligned test models. Under ISO 26580, this output is defined as transient digital data. These assets are entirely disposable. They are never checked into a version control repository. If a bug is found during testing, engineers do not patch the generated product. They patch the central superset, delete the transient product instance and regenerate it. Individual products no longer carry their own configuration management overhead. They operate as instantaneous mathematical outputs of the factory. This rigorous centralization has a significant macroeconomic impact when deployed on massive defense-scale systems. This is the Navy Combat System Engineering Development Site, anchoring the Aegis weapon system, a prime example of operating at maximum engineering scale. We quantify this by plotting number of products against total engineering cost. With traditional methods, maintaining separate code bases causes cost to balloon exponentially. But with feature-based PLE, the cost curve flattens out, a phenomenon known as superlinear cost avoidance. Because maintenance and testing only occur once inside the core superset, the marginal labor required to add a highly complex new variant stays nearly constant, regardless of the product line's total size. Mastering this superlinear curve provides the only sustainable mechanism for organizations to scale their product portfolios without collapsing their engineering budgets. This economic efficiency becomes a critical survival tool regarding automotive functional safety standards, like ISO 26262. Historically, functional safety audits were an operational nightmare. Engineers had to manually prove an unbroken chain of traceability, from risk assessment to final code, for every single distinct vehicle variant separately. With an ISO 26580 factory, this is automated. In this ISO 26262 traceability matrix, hazard analyses and validation tests are securely embedded as conditional variation points. A single generation event outputs perfectly traceable compliance artifacts across 50 vehicle variants simultaneously. ISO 26580 uncouples a product's logical identity from its physical engineering assets. For organizations managing vast complexity, this automated logic is the prerequisite for digital engineering at scale.